Matthias Schuler is going to take his place as a keynote. He had only a few minutes well, short notice to get his keynote ready. So that's what he did. Unfortunately, he didn't have the time to give me a bio, so he's going to do that himself. So I want to have a great applause for Andreas for this presentation here.
Thank you, Marielle, for the kind introduction. And also good morning from my side. Thanks for coming to the session after the beautiful conference dinner we had last night. And I heard there were 7 persons enjoying sunrise in Zurich. It must have been a very special experience. So yeah, actually I was asked at short notice, so it will be a lot of improvisation. And at the bottom of my backpack, I found a USB stick, and on the USB stick, I found some slides. So we'll have to do with what we have today. So it's all about materials. I'm a trained physicist. I had a master's degree from the University of Michigan at Ann Arbor. I hold a PhD degree from the University of Basel. I've been working for many years at the LESO Institute. It's a laboratory of solar energy and building physics at EPFL. And we are very much concerned about light, interaction of light with materials, and development of novel materials for the building envelope. What can we do with daylight on the building facade? There is a transparent part of the building, the windows, the glazing. So we can filter the light, we can redirect the light, we can control the intensity of light. We can also harvest the energy on the opaque part of the facade. On the facade cladding, we can create electricity, we can create thermal energy. And all this can be done with novel materials, materials which are based on novel micro and nano structures. So it's very much situated in an interdisciplinary field in between physics, lighting, daylighting, material science. There are many aspects. And I try to point out where we had already interactions with the members of the Daylight Academy. So when you look at traditional farmhouses in Switzerland, you might notice that in old farmhouses, the windows are always very small, especially on the north facade in old buildings. And back then, a window was always considered as a leakage in energy because they had simple glazing, single glazing, maybe first versions of double glazing. There's problems of tightness and so on. So the window would be minimized. And there was not so much daylight inside the building. And in the recent 20 to 30 years, it changed completely because there was kind of a soft revolution in windows. Windows, it's like reinventing the wheel. In the last 30 years, the window was reinvented by architects, engineers, and scientists. And now we have much better window technology available. First of all, we have tight windows today. Then we have special coatings, invisible coatings on the windows. These coatings have a wavelength selective property. They transmit daylight, the visible part of the daylight, some part also of the infrared radiation, and they reflect the heat radiation. So they are a heat mirror, and they have the property of low thermal emissivity, so they keep the heat in the building in winter in our latitude. Or in Dubai, for instance, they keep the heat outside the building, and you save either on air conditioning or on heating. And thanks to this kind of silent revolution in window technology, we have now buildings with large openings. The building is opening. Now the visibility outside, you have daylight coming in. And we are all concerned about health, circadian rhythm, well-being of the building users. So having daylight in is something which is really new in our development of architecture. So you have the question of visual comfort, for instance. You have the question of overheating, thermal comfort, and so on. And especially when you have highly glazed buildings, then the question of overheating becomes very, very important. Because in such a building, when the architect would not think about solar protection, you would need a lot of energy for cooling the building in summer. So you have to think about how to manage the solar heat gains and it becomes a multi-criteria decision. So you need visual comfort, you want to avoid overheating in summer, you want to have some contribution of solar heat gains in winter. So it becomes also more complex. And we have to think what we can do about the management of the solar heat gains and also the management of the daylight in the building. There is some idea from the group. When I was at the University of Basel, I had the chance to work with Peter Oelhafen, and he brought up a new idea. He suggested a new transmission function for windows. The idea would be to have a maximum of visible daylight in, to maximize the visible transmittance of the window, and to allow only for minimum solar heat gains in order to avoid the overheating. And what industry does typically for 20 or 30 years now is they would create a transmittance peak in the visible. It's just a curve with one bump, and it peaks at 550 nanometer in the visible light. So this curve is the dashed and dot line here in the image. Now, he thought about it, and he thought, why don't I calculate the optimum transmittance curve? So he made a mathematical approach, and he found a curve with two maxima, with two bumps, like an M. This is this M-shaped curve, which is shown here. Okay, good. Which is shown here, the solid line. And that was really counterintuitive and unexpected. We understood much later why it was like that. It is because extreme blue light and extreme red light, they are just at the wings of the V lambda curve, the curve of the sensitivity of the human eye. So it costs a lot of energy to produce this visual appearance. So if you just skip a little bit of the blue and red light, it would be a lot of heat gains less. And then we get a greenish tint. And in order to compensate for the greenish tint, we make a minimum in around 550 nanometers. This explains this M shape. And the gains, the theoretical gains of this is amazing. So you can gain a factor of, so what we would calculate is then the ratio of the energetic transmittance and the visible transmittance. And that would change about, it would improve about a factor of 150%, 1.5. And just by theoretical consideration, and nobody else before him had this idea, because the industry was just doing what they were doing all the time. And he had, like, as a physicist, he had the perspective which allowed him to think about the problem from the real beginning and make a mathematical approach of that. Now, today, at the 4th floor of the Physics Institute in Basel, it is equipped with such glazing, which is made like this. Always very difficult to organize with industry to have some thousands of square meters of special production for your new prototype coating, but they managed. They made an arrangement. They equipped the building, and now the glazing is there. Now, in order to put such a product on the market, there's even more inertia, and let's see whether one day we see this really happen. But I think the idea is brilliant, and it's a really brand new original idea. The other possibility to manage solar heat gains and to manage glare would be switchable glazing. Glazing of which you can control the solar transmittance, the energy transmittance, and also the visible transmittance. There's been electrochromic glazing, switchable glazing around for some time. And there was a clear drawback until recently. It was these materials were based on a gel-like, liquid-like electrolyte. It is an electrochemical cell. It's like a micro battery. And they needed a jelly-like electrolyte in between two glass panes. Now, we tested at the LESO Institute. We had some tests of that. And we realized that after some years, the gel, like the gas phase of the gel, would just diffuse out gas. And then we would have problems at the edges of the window. So there would be failure after some time. And in the building, we need a stability of the materials for 30, 50 years or even longer. And this is also a recent development that the devices nowadays which are used shift to solid ion conductors. There's a lot of research in batteries going on, lithium-ion batteries, and the materials which are found from lithium-ion batteries, They are also useful for electrochromic windows. And now we can produce such windows without even using this jelly-like electrolyte, which might outgas after a year or so. Still, the way is, we have a long way to go. So when it is tinted, it's always blue. It takes 20 minutes to switch. The switch should be much stronger. So it should be brighter in the bright state, dark in the dark state to have really glare protection. And we recently started some collaboration with the Lipid Laboratory, with Jan Winold, Marilyn Anderson, and Jena Snein. She was presenting yesterday, a flash presentation on poster. And we started looking into the question, into this issue about what is the spectral properties of such electrochromic glazing in the darkest possible state, and is it sufficient for glare production, for glare protection? And I think these devices still have to improve a little bit. So these devices must become better in performance still, and also they should become cheaper in the long term, but there's some hope if there's a market implementation and the learning curve, then such products become cheaper and cheaper in time. So concerning the opaque part of the facade, we are already at the level where we have a widely visible demonstration building, the Copenhagen International School. This is the building which features maybe the largest photovoltaic facade on this planet currently. It was all done with the technology which was developed in our research group, the chromatics technology. We developed colors which are very energy efficient. And the way we do this is we base the colors on thin film interference, on the interference of coherent waves, which are produced by structure. So it's interaction of daylight with structure, nanostructure, microstructure, and wave interference. This is a physical color, not a chemical color. There's no absorption or pigment needed. And that is the explanation why these interference colors are so energy efficient. So if we would conserve, in the laboratory, we can conserve 95% of the produced electricity and still offer a very wide range of colors to the architect. And the architect can choose from the color, so you can really have a very good quality of architectural integration in the building. In nature, there are many examples for structural colors. The most famous one and the most widely cited one is the blue morpho butterfly. And many researchers love this butterfly because it has blue wings, and the color of the wings are produced also by structure and wave interference. So I have some other example of nanostructures in nature. So you might have noticed that geckos stick to walls which are really, really flat. And this is also possible because there are nanostructures on the little feet of the gecko. So you have this structure, the cetal arrays, and at the top of the ceta you have the spatula, and this allows really the gecko to suck on the wall and stick on the wall. So this is a function, a macroscopic function. The macroscopic object would not fall down, which is induced or made possible by a nanometric structure. So this is quite amazing. There is another widely cited example. This is the lotus flower. The lotus flower is very famous because the leaves are always very clean. And researchers are fascinated by the self-cleaning effect of the lotus flower. So how does it work? So you combine the property of hydrophobicity with roughness. And when you introduce roughness to a hydrophobic surface, you increase the amount of surface, and then you need more free energy in order to form the interface. So a droplet would not like to do that. A droplet would like to minimize the contact with the leaf. So that would result in a very special contact angle, and the droplet would just bounce off and wash the dirt away. This is a very sticky paint, red paint, which would not stick to the lotus leaf. And now the dream would be, why don't we make buildings like this, which are self-cleaning? Why don't we make photovoltaic modules, which are clean forever and to maintain a high efficiency forever? That would be a beautiful dream. And we actually in the laboratory, a close colleague of mine, he made such samples. So he created a rough surface and with aluminum oxide needles, and then he would deposit a hydrophobic Teflon-like kind of film on top of these needles, and then he made beautiful videos of droplets bouncing off and washing the dirt away. So on the left-hand side, you see the sample with the treatment. On the right-hand side, just a rough surface, and on the left-hand side, the rain washes away all the dirt. So now it works in nature because the hydrophobicity is based on wax, which is produced by the plant itself, so the plant can regenerate itself. And if you make it as a material and you hope it will stay forever or for 50 years, then you have the problem that you need to regenerate the soft hydrophobic material. But we learned today, also yesterday, in the laboratory of Arthur Brown, that they are working on self-healing materials, and I think there is exciting research upcoming in the field of such materials. Now, we are very much interested in metal clusters. Metal clusters are also a favorite topic of physicists working in a branch called photonics and plasmonics. So these metal clusters have rather free electrons, and there's a possibility there's the surface plasmon resonance, an oscillation of these electrons on the surface of such clusters. And this results in interesting properties when daylight interacts with such metallic nanostructures. So you can have them substrate supported, or what we need them embedded in a film, embedded in a coating, as for solar energy coatings, for solar thermal collectors. So how to treat those theoretically? You can make a model. Say you mix two materials, A and B, for dielectric crystals. Let's take two different type of ceramics, for instance, and mix them. Then you would have bubbles or balls of two materials, blue and yellow. You would mix them, and then you can make a so-called effective medium approximation. So one ball, one sphere of material A or B is embedded in an homogeneous medium. For this situation, you can write down the Maxwell equations and solve them with a pencil and a paper, and you find a answer to the problem of what the optical properties of the resulting material would be. If you have metal clusters, then it's especially important that you take into account the interface of the metal and the ceramics. So because you have these free electrons at the surface, this surface plasmon resonance, so you need really direct interfaces between the blue and the yellow regions. So that is why in this model, you need coated spheres in order to model what happens. And also this can be integrated with a pencil and paper. But in the recent 10 to 15 years, this field evolved very, very quickly, because now we have much higher computing power available than 10 years ago or 15 years ago. Today, we have the means of calculating complex optical structures very quickly, and it would have taken much more time just 15 years ago. And today we can calculate complex shapes on the nanometric or micrometric scale with high accuracy by an approach called FDTD, for instance, finite differences in the time domain. It's a calculation approach, and it works really well with today's computing power available. And what is new here is physicists were always struggling when the size of the structure was much smaller than the wavelength. Then you could do this effective medium approximation and write down a theory. When the structures were much larger than the wavelength of the light, then you could do geometrical optics. That was working very well. But when the structure was about the same order of magnitude of the wavelength of the light, then the physicist expects a lot of diffraction effects, and it's hard to solve analytically. And that is why today we have the possibility to compute this and study proximity effects of clusters, finite size effects, and so on. Currently, recently we started working with Christian Frankhauser on biological problems, on interaction of daylight with plants. And this is for us completely new topic. And is something which is for me absolutely fascinating, because here we link our physical tools to biological research questions, which for us is absolutely new and passionate. So there are various ways to make nanostructures. You can use top-down lithographies. You could basically take a chunk of material and cut it into small pieces. So creating it from top to the down. You can also take individual atoms and assemble them. For instance, the physicist would do it with an AFM tip, with a microscope tip, and push together atoms and write letters and so, or might make atomic scale devices. The chemist has other ways of making a molecular chemistry. And there is also the possibility of growing thin films in a self-organized way. And this is especially interesting for us, because on the left-hand side, you have both parallel processes. You can cover a large surface at the same time. On the right-hand side, you have the idea of building up atom by atom. And now we are even combining making thin films and then structure them later. So first we would use the bottom-up approach and then the top-down, and then we can even scribe structures in our coatings. This is how our laboratory looks like. So we have a little snapshot of the physicist. So we have an introduction chamber. We would introduce an object to be coated into this introduction chamber, then transfer it to the deposition chamber, make our deposition process, which is based on a cold plasma, the process called magnetron sputtering. And then we have surface analysis techniques such as electron spectroscopy. This gives us a lot of information on the electronic properties of the materials, and the optical properties of a material are a consequence of the electronic properties. So solar energy is about this, covering a large surface with a small amount of materials. So we make thin films. It's related to optics. It's related to electronics. You start standing up. Am I running out of time? Yes? Oh, no. Okay. Anyways, it's all improvised. So this is how our lab looks like. And this is how in industry it looks like. So it is implemented in the real scale. And now maybe I just jump all these slides. I have just to mention that we made these colored solar thermal collectors. More recently, it's more photovoltaics. We have the NEST building here on Amper campus, where some of the parallel session took place. And the NEST building, there's one module we did together in a group with Jonis Cartesini, who was coordinating with Marilyn Anderson from Lipid. Jan Wienold was there. There was Raphael Campagnon also. And we had Lutz Architects and the people of Amper, of course. And we were building this Solace module. And when you look and when you leave this conference, maybe you can get a glance at the building. There's this bluish, greenish facade on one of the modules. This is made with our technology of colored photovoltaics and colored solar thermal. There's one I really would like to, I jump all these things, but I would like to speak about this because we have a pioneer here in the room who was working on this. So this is an idea of how to concentrate daylight. Daylight in our latitude, we have many days like today, it's in many cases just diffuse daylight. Now concentrate direct daylight, it's very easy. You can take a mirror or a lens and focus it. But if you have a diffuse day, it's hard to concentrate. And there is one concept allowing this. This is the concept of the photoluminescent concentrator. This was proposed by the former director of the Fraunhofer Institute, Adolf Götzberger, and was introduced on the basis of organic dyes. And more recently, researchers came back to the topic. How would this work? The energy would be incident on a slab of material. The dyes would absorb the energy and they would re-emit in a fluorescent way the energy, and 2/3 of the daylight would be captured and concentrated within the slab by total internal reflection, and at the edge of the slab you can harvest concentrated daylight. One of the very, very few principles which allow us to concentrate not only diffuse, but not only direct, but also diffuse daylight. And recently the researchers came back to that because there are new materials available, quantum dots. And I would like to show this slide because we are with Brian Norton today, and Brian and his students were doing great way in simulation and analysis of these devices, and also in synthesis of such materials. So they had he and his postdocs and PhD student did great pioneering work in this field. And that is also one of the manifold interesting applications where size is important, because the color of these quantum dots, these semiconductor nanocrystals, depend really on the size. So if you have like the quantum dots which give the blue light emission have 2 nanometers in diameter, and those giving the red emission 8 nanometers in diameter, and the color depends on the size only. It's a particle in a box problem known for physicists. So now let me jump to the conclusions. Nanotechnology is a field which is evolving. There's a huge community of researchers active in the field. EMPA here, our host today, is at the forefront of research in nanotechnology. There are many researchers active. There is a lot of innovation happening. New materials are created, invented. And we are especially interested in how does this new material, or these new materials, how do they interact with daylight? And can we take benefit for using such materials for the building envelope and offering to the architects new functions, as the low emissivity coating gave us the option to have more daylight in the building. Now we can even offer energy efficient colors to photovoltaic, to solar thermal. We can make windows which redirect daylight with micro mirrors, which are invisible. We can create windows which keep in the heat, but transmit the microwave radiation of mobile communication and so on. So there are plenty of applications. Here is a short overview. So you can have broadband anti-reflection for active solar. You have collector glazing for facade collectors and for facade modules. You can have highly durable absorber coatings for industrial process heat. There's a lot of CO2 emissions linked to industrial process heat, which we could save by solar energy. We have now new generations of electrochromic windows. We have thermochromic coatings for overheating protection of solar thermal collectors, highly efficient solar cells based on nanostructures, and continuous solar concentrators, allowing to concentrate not only direct, but also diffuse solar radiation and daylight. I would like to thank my close colleagues at the LISO Institute, which is headed by Jean-Louis, and the people in my group. I would like to thank all our laboratories on campus EPFL. Hopefully next year we meet at campus EPFL. And there are 300 labs on campus, and we have many-fold possibilities for interaction with these laboratories. I would like to especially thank the University of Basel. I've seen there is a strong team from the University of Basel here with us today. And they taught us a lot on how to communicate science yesterday. And I was really grateful for that. As old alumni from University of Basel, we have contact to SPF Rapperswil, which is not far from here, for the solar thermal collectors. We are grateful for our funding agencies, of course, and our industrial partners. And I would like to thank you for coming here, for being here, in spite of the fact that the night was maybe short. And I thank you for your attention. I don't know whether we have time for questions, but if there's time, I would be happy to answer those.